In these next videos, what we're going to do is start looking at a kind of different version of limits. They're really the same thing, but now we're going to be looking at what happens when one of our variables maybe isn't approaching a real number. In that original definition of a limit, we talked about how our y values have to approach a single real number, L, as x approaches a, and a was a real number as well. So we're going to start looking at what happens when we change those values to maybe possibly be infinite. The beginning of this, we're going to introduce things by discussing what happens when you divide by zero. We've got two types of division by zero. Then we're going to take a look at infinite limits. We'll take a look at them graphically, numerically, and analytically. That seems to be a theme so far of analyzing things in three different ways. All right, so let's start this thing off with division by zero. So here we have this division of functions. We might remember that with a quotient like this, we can put the limit up in the numerator and the limit in the denominator. And if this limit on top and bottom are both zero, then we said that limit might still exist. It maybe doesn't. We call this an indeterminate form. Oh, I can't spell. Indeterminate form. And we'll come back to these later on in the semester and talk a ton about indeterminate forms. For now, the key that we have is to just do some algebra. Whether that's factoring, whether it's using that conjugate trick that we talked about, or dealing with some fractions inside of fractions, we're going to do some algebra to come up with a second function that's exactly the same as the first everywhere except at this x value that we're approaching maybe. And that might make things a little easier to deal with. We have this other way of dividing by zero, though. So if this first one is 0 over 0, I'm going to call this one like a number sign over 0, where specifically we mean not 0 divided by 0. Some other real number, 7 over 0, negative 15 over 0, pi over 0, something like that. If that's the case, then we know that limit does not exist. So that's the first thing. We get a ton of information right away. What we're going to notice is that these kinds of limits are going to always result in either a two-sided or one-sided infinite limit. So we're always going to notice that this infinite limit shows up in a case where you have a non-zero number in the numerator and 0 in the denominator. So let's think about this two-sided and one-sided idea of an infinite limit. Here's our intro to infinite limits. Infinite limits are when the y values go off to infinity. So again, we're going to suppose that we've got some function that's defined for all the x values near a value of a, blah, blah, blah. Same setup as before. Now, though, instead of f of x getting arbitrarily close to some real number L, we're going to say maybe f of x grows arbitrarily large whenever x is sufficiently close to a but not equal to a. Or we could say f of x is going off to infinity. Then we can say this limit is equal to infinity. The equal sign is sometimes confusing because you can't have something equal to infinity in terms of function values. So we're not saying that the function values are equal to infinity. We're saying that the limit itself is. This is the thing that we're getting arbitrarily close to. So arbitrarily large means that f of x goes off to infinity. We could have the same thing, but if f of x is negative and grows large in magnitude, this is just a fancy way of saying it gets small, although we don't want to say small because small kind of means close to 0, right? We mean it gets really, really, really negative. It dives off in the negative direction. So it gets really large in size, in magnitude, but it's negative. Whenever x is sufficiently close to a, we say that our f of x approaches negative infinity, or this limit is equal to negative infinity. Well, notice that even though the left and the right side limits might have the same behavior, whether they're going to infinity or negative infinity, these infinite limits do not exist. Infinity is not a real number, and in our definition of limits, we said that our function values have to get arbitrarily close to a single real number L. So this is not the case here. So infinite limits do not exist. All right, so let's go ahead and discuss the behavior here. We'll try and figure out what is f of x doing around 0, or really we'll say, what's this limit as x approaches 0 of 1 over x squared? We could think about this graphically if you want, or we could plug in some test numbers, or we could just try and figure out what's happening here. Maybe let's just try and figure out what's happening. Actually, I'll draw the picture of the graph. So here's our sketch of our graph, our axes that we've got, and I'll draw our graph in blue. this is 1 over x squared. You've probably seen this function before. It's probably not new. We have this nice vertical asymptote right here at x equals 0, and we've got a horizontal asymptote right here. And what we care about is what's the behavior of our function around 0. What's our function doing? Well, we've got this vertical asymptote. It seems like our function is going up on both sides. What this sounds like is that the y values are growing arbitrarily large, right? So maybe what we'll say is that this thing is infinity. Cool. All right, similarly, let's discuss this one. So let me draw a picture of the graph again, and I'll write out the limit that we're looking at. This is just our regular old reciprocal function, but it got shifted over by 1. So this is what we've got here, where we've got this nice vertical asymptote right here at x equals 1. And the limit that we care about is the limit as x approaches 1 of 1 over x minus 1. So we're saying, what's the behavior of our function here? What we'll notice is that on one side of x equals 1, our y values are going up. They're getting arbitrarily large. And on the other side, our y values are going down. They're negative and growing in magnitude, right? And so we can't say that this is equal to infinity or equal to negative infinity. So what we'll say is that it doesn't exist. Now, what I want us to remember is that the limit before doesn't exist either. But we have some idea of how to describe the behavior of it. It's an infinite limit. The two sides go off to infinity, so we can give a bit more detail about how it doesn't exist. We can give a two-sided limit statement that describes its non-existence. Here, we can't. We'll be able to give one-sided limit statements that describe how it doesn't exist, but I want you to keep in mind that this limit doesn't exist not just because the left and the right sides don't match. That happens to be true, but even if they do, like in this case, they both go the same direction, that doesn't mean this limit exists. Infinity is not a real number. Okay, cool. So here's our one-sided infinite limits. We can define one-sided infinite limits pretty much the way that you'd think it does. We'll say, suppose that your function is defined for all the x values less than a if f of x grows arbitrarily large when x is sufficiently close to but less than a, then we can say the left-sided limit goes off to infinity. And then you can just tinker with the less thans and greater thans to get left and right side limits that are infinite. So what we'll notice is in that picture that we had of the reciprocal function, 1 over x minus 1, we have some one-sided limit statements that we can use. So here was our picture. We had this vertical asymptote here. And while we can't say that the two-sided limit is anything specific, what we can say is that the limit as x approaches 1 on the right of 1 over x minus 1 is infinity. And we can also say that the limit as x approaches 1 on the left of 1 over x minus 1 is negative infinity. The left-sided behavior, the y values are going down. On the right, our y values are going up. So graphically, this isn't too hard to deal with. So one last thing to notice is that these infinite limits match up with vertical asymptotes, which is great because we know a ton about vertical asymptotes from our algebra classes. So let's get into some approximations of these infinite limits. It's really easy to do this graphically, right? We could go ahead and label a whole bunch of limit statements on here. Right off the bat, I can look at this one and I can see we're going down in both sides of this asymptote. So the limit for this function as x approaches negative 2 is negative infinity. Right here, you'll notice that on one side you're going up and on the other side we're going down. So we'll say the limit as x approaches 1 on the left of f of x is negative infinity, and the limit as x approaches 1 on the right of f of x is positive infinity. And then you can see here at 3, both sides go up, so we'll say that the two-sided limit is infinity. Now, none of these limits exist, right? None of them are going to real numbers. If we had to give a two-sided limit statement about what was happening at 1, this spot here, the most that we could say is that this limit doesn't exist. Now, we could say that for all the other ones as well, but we can say more than that for these two-sided limits. We can say, sure, the limit doesn't exist, but the y values decrease down and they chase negative infinity as you get close to this x value. And similarly, as you get close to the x value of 3, our y values increase. They look like they're unbounded. They're going up to chasing infinity. So we can give a bit more detail about how they don't exist. We can do this numerically as well. Let's say that we have some information about a function, whether we found this by plugging these values into a function rule or we were just given these points. We can take a look at the left-sided limit here and try and see what do the y values look like they're doing. It's hard to tell exactly, but it seems to be pretty convincing that these y values are getting really, really, really negative, right? This gives us a lot of good evidence that for this function, our limit is negative infinity on the left, and on the right, we have the same thing. They're getting really, really negative. So we might say that this two-sided limit is equal to negative infinity here. Now, this is an approximation because I don't actually know that these y values are going to get arbitrarily large or arbitrarily negative. I know that they get really, really, really negative, right? But I don't know, maybe these do stop at like negative some huge value that I have a hard time even imagining, right? Like negative 10 to the 15th exponent. So that's a 1 with 15 zeros after it. Maybe the negative version of that is where this function's going, but it's hard to tell. I'm going to just assume that they're getting really, really, really negative, maybe going unbounded. I'm assuming that, so it's an approximation. All right, let's think of how to evaluate these infinite limits. So what we're going to do is we're going to notice the main idea here is that if you can write a function as a product or a quotient of a bunch of pieces, we can track the sign through that really easily. Because I know what happens when you multiply two positive numbers together, or divide a negative by a negative, or multiply a positive by a negative. I know the sign of all those things. So what we're first going to notice is that if we can tell that this is going to be an infinite limit, because, well, maybe I'll go to the two-sided version. If you put 1 into here, we get 2 minus 1, that's 1, times 1 plus 3, that's 4, over 1 minus 1 squared, that's 0 squared, times 1 minus 5, that's negative 4. I've got 4 over 0. I'm going to call that some number over 0. I know that this is an infinite limit. I know there's a vertical asymptote at this x value of 1, and so we can start analyzing this. I know that my left and right-sided limits have to either be positive infinity or negative infinity. So, knowing that, I can go through and just chase the sign here. Keep an eye on this. If x is approaching 1 from the left, that means x is smaller than 1. So, let's just track through the sign on this. 2 minus x. This is 2 minus a number a little bit smaller than 1. That's going to be positive. A number a bit smaller than 1 plus 3, that's going to be close to 4. That's going to be positive. You can see that because our numerator was positive. So this is going to be a positive times a positive. Then I've got x minus 1, a number a bit smaller than 1, minus 1. Notice this is going to be a really, really small negative number, but we're squaring it. All right, and now I've got something close to 1 but smaller than 1, minus 5. That's going to be negative. So I've got positive times a positive over a negative squared, that's positive, times a negative. That's positive over negative, that's a negative value. If the only options were infinity or negative infinity, because we knew that there's an infinite limit going on here, and I just showed that my sign has to be negative, that means this left-sided limit is negative infinity. Similarly, for the right-sided limit, we can track all the signs down. Now we're looking at x values that are a bit bigger than 1. 2 minus a number a bit bigger than 1 is still positive. 1 plus 3, or a number a bit bigger than 1 plus 3, is still going to be positive. Again, our numerator was positive already, so we knew that was going to be positive. But our denominator was close to 0, so let's see what sign it is when x is a bit bigger than 1. Now we have something a bit bigger than 1 minus 1. That's a positive number. But remember, we're still squaring this. So it kind of didn't matter if this was positive or negative. When we square it, it becomes positive anyways. And then we have a number a bit bigger than 1 minus 5. That's still negative. Would you look at that? That's a positive over negative. This is negative. So that means this limit has to be negative infinity. So our two-sided limit, we can go ahead and say this is negative infinity because that's the behavior on both the left and the right. Now remember, this limit doesn't exist, but we can at least describe how it doesn't exist. Let's do the same thing again with the cotangent function, and we'll just notice that cotangent of theta is really cosine of theta over sine theta. So we're going to be thinking about the sign, positive or negative, of these two trig functions, cosine theta and sine theta. Let me grab a little unit circle for us, just so we can get a good feel for what's going on here. I'll draw my axes. And remember, sine theta is the y value, cosine theta is the x value of these points. So we're going to look at a value for theta that's slightly less than 0. That's an angle right here. I'll notice my x value is positive, my y value is negative. That means cosine of theta is positive, sine of theta is negative. This thing is a negative sign. Whoops. So if this is actually going to be an infinite limit, which I probably should have showed us that it was going to be right off the bat, let me remind ourselves. Cosine theta over sine theta sure looks like it's going to be 1 over 0, right? Sure looks like we're going to have an infinite limit. Or you might remember that the cotangent function has a vertical asymptote at 0. We've taken trig before. We should know that kind of thing. So we've got this negative infinity behavior on the left. Now what we'll notice is that when we think about angles that are a bit bigger than 0, we're looking at points in this quadrant. And you'll notice that cosine and sine are both positive there. So this is positive over positive, meaning the sine is positive. And so this behavior is infinity. The left side limit is negative infinity, right side limit is infinity. So all we can say for this two-sided limit is that it does not exist. If we think about the picture of the cotangent function, this should make a lot of sense, right? We've seen this function before. We know it has a vertical asymptote at 0, and we know that on the left it goes down, and on the right it goes up, and that's because our cotangent function looks like this. Over and over and over again. So the behavior of our cotangent function we can describe using limits. That's all we've got for this. Infinite limits aren't too bad. I like to do this sign argument to follow the sign through things analytically, but we can normally get a really good idea of what's going on if we understand what's happening with the graph. Graphical approximations are really great as well for these. But remember, you can just track the sign through this, and if you know there's an infinite limit happening, all we care about is if it's positive infinity or negative infinity. In our next video, we're going to look at what happens when the x value goes off to infinity or negative infinity. In this one, we were thinking about the y value shooting off to infinity or negative infinity. So in our next one, we'll try and figure out what happens when x goes off to infinity or negative infinity.